R1 is a simple resistor connected between these two terminals, and we just happen to have a current source going this way called I2. I2 is known, V1 is known, R1 is known, and we would like to calculate Ix. So how do we do that? Well, we have to write a KCL at this node. Right? At this node, we have 3 branches meeting. This branch, and that branch. Okay? All right. This branch carries a current equal to I2. That's the job of the current source. It doesn't matter what this guy does. It doesn't matter what this is. This branch always wants to carry I2. So that's for sure. So we're going to put an arrow here, call it I2, to make sure we remember that. Okay? This branch has a current Ix. We don't know what it is. We have to calculate it. How about this guy? Do we know the current through R1? Well, we know the current through R1 only if we know the voltage across R1. Do we know the voltage across R1? Yes, because this voltage is the same as this voltage, right? We have a battery connected across a resistor. The resistor has that amount of voltage on it. So the current through R1 is known, is equal to this voltage, which is V1, divided by this current, according to Ohm's law. So this current, I will change the color of my pen to make it a little clearer. So this current is equal to V1 over R1. Ohm's law. Okay, so now we are ready to write our KCL at this point. Of course, we have to be very careful with the polarity of the currents, the signs of the currents. So one thing you could do is you can say this current plus this current plus this current is 0. Or you can say the sum of currents flowing into the node must be equal to the sum of the currents flowing out of the node. So you could say this, which is flowing into the node, plus this, which is flowing into the node, is equal to this one, which is flowing out of the node. It's the same thing, it's just your preference. You can either write it like this, or you can say it as I do. So I would like to do the latter because it's more intuitive. So I'm going to say I2 flows into the node, Ix flows into the node, but I1, this current flows out of the node, the red one. So that should be V1 over R1. Okay, so that means that Ix is equal to V1 over R1 minus I2. And that's what we were looking for, right? V1, R1, and I2 are known, so that's what we get for Ix. All right, the circuit is pretty simple, but doing these things takes some thinking, right? Before we just jump in there and write equations and so forth, we have to have a feel for what's going on in the circuit. Who's delivering current, which ways the current might be flowing, and all that stuff. Okay, all right, so that was a quick note on KCL. Let's see if I have anything else. Okay, let's talk about KVL now. All right, so it's important to understand that KCL refers to a node in the circuit. A node is defined as where some branches meet. So what it says is that the currents flowing into the node have to be all add up to 0 algebraically, or the currents flowing into the node should be equal to the currents flowing out of the node. Now, KVL does not relate to a node, it relates to a loop. A loop means a path through the circuit that might traverse a number of devices before it returns to its origin. So we're talking about the loop. So for example, you have something like this, you have something like this, something like this, something like this, etc. There are all sorts of things connected to these things, right? And we pick one of the loops, for example, this loop here. And what KVL tells us is that this voltage plus this voltage, excuse me, this voltage plus this voltage plus this voltage plus this voltage is 0. Okay, so that says sigma V equals 0. So again, it's important to understand that KCL relates to the currents going into a node. KVL relates to the voltages in a loop. A loop consists of a path through some devices that goes back to its origin. So we start from here, for example. We go this way, we go this way, we go this way, and we come back to where we started. Okay, that's KVL. Now, it turns out that the KVL also has an intuitive explanation. KVL is really based on conservation of energy. And maybe the way to think about it is the following. So imagine that we have a hill and we push a bowling ball up on the hill. So in taking the ball from here to here, we gave energy to the ball. Now we let the ball go. So what happens? It accelerates, it comes down. So by the time it gets here, it has gained that energy back, right? So now it has an energy that is equal to the energy that we gave it. So imagine that this hill is so resistive, or I should say it has so much friction, that by the time the ball comes back here, it has 0 velocity. Then the energy that we spent taking this back up was lost as it came down. So the net energy as we went from here to here is 0. And that's equivalent to saying the net voltage difference from here as we go back to here is 0. Okay? But anyway, the key point here is that KVL is really based on conservation of energy. Okay, so let's just look at an example to understand how KVL is applied to a circuit. So here's a quick situation. I have a battery here. I'm going to call this V1. And then I have a resistor here. Call it R1. I have another battery here. Call it V2. Okay? And my objective is to find the current that flows this way through the resistor. We'll call that IX. How do we do that? Okay, well, so what we know are V1, V2, and R1. And what we don't know is IX. Well, we have we can use KCL here because we have a loop. So we're going to start from here and add up all the voltages as we go along, and then add the total sum, equate the total sum to 0. Now the only thing we need to know is the voltage across this resistor. How much is that voltage? Well, Ohm's law says that if you multiply the current by the resistance, you get the voltage. We call the current IX for now, so IX times R1 is the voltage across R1. Now, which side is positive, which side is negative? Because IX is flowing from left to right, then the positive side of the voltage will be on the left, and the negative side of the voltage will be on the right. So there will be a voltage from here to here, and that voltage is equal to IX times R1. So now it's pretty quick, right? We're going to write a KVL. Start from here. This voltage is how much? Because I'm going from negative to positive, it's minus V1. So I will write minus V1. This voltage from here to here is how much? IXR1. And it's plus IXR1 because I'm going from plus to minus. So plus IXR1. And then here, I'm going from plus to minus. So that's plus V2, and that's equal to 0. So now we can find IX. So that means that IX is equal to, we take this to the other side, we have V1 minus V2, over R1, V1 minus V2 over R1, that is the current through the resistor in this particular circuit. Okay, so that's pretty cool. The combination of KCL and KVL allows us to solve any circuit under any conditions. These two suffice. We have other methods of solving circuits, but you don't even need to know those. As long as you have these two, you can solve any circuit under any condition. So they are very powerful because they're based on fundamentals: conservation of charge, conservation of energy. Okay, let's see. All right. Well, let me give you one more example of using KVL. Let's see here. Okay. So I'll insert a page and I'll add another example here. Okay. All right, well, okay, so here's another circuit. We have a voltage source, which we call Vx, and we have a resistor R1, and then we have another resistor R2. Okay, and I would like to find the voltage across R2. So I know Vx, I know R1, I know R2. I would like to find the voltage across R2. So this voltage, we'll call this V2. The voltage from here to here. Okay, how do we do that? Well, as usual, we will try to write a KVL, and because we have resistors, we probably have to use Ohm's law as well, right? Okay, so let's think about this for a little while before we jump in and write equations. Okay, we call this voltage V2. We don't know what it is, but it's called V2. So if the voltage across R2 is V2, some amount, how much is the current through R2? Well, Ohm's law says, if you know the voltage and you know the resistance, divide the voltage by resistance. That will give you the current. So what I do know is, I'm going to change the color to maybe this. What I do know is that this current, the current flowing through R2, is given by the voltage on the resistor divided by the resistor. So V2 over R2. Now V2 is unknown, but eventually, hopefully we'll find it. And the current through R2 is V2 over R2. So far so good, right? Okay. Now, if I know the current through R2, do I know the current through R1? Well, I know the current through R2. Do I know the current through R1? Now we have to resort to KCL. KCL says current cannot disappear. Whatever flows through this wire to this node has to go where? Has to go down. There's no other place to go. So it turns out that the current through R1 and the current through R2 are actually equal. And that makes sense because I think you have seen series resistors. And these two are in series, you can see that, right? So they have to carry the same current. But in any case, it's a KCL at this node, right? This current has to be equal to this current because it has nowhere else to go. So what I can say is that the current to R1 is also V2 over R2. So far so good? Okay. All right. If I know the current through R1, do I know the voltage across R1? Yes. Ohm says multiply the current by the resistance to find the voltage for a resistor, right? Okay, so this resistor says I carry a current from left to right equal to V2 over R2. Therefore, I will sustain a voltage equal to the current times the resistance. So there will be a voltage drop across R1. I'll change the color again to maybe orange. So there will be a voltage drop from here to here, right? From here to here. And that voltage is given by this resistance times the current through it. So that voltage is now equal to R1 times the current through it, V2 over R2. Okay, so I hope you're following the thought process here, right? Rather than just write a bunch of equations and see how we solve them, we try to see what the circuit is doing and gradually on the circuit write scribble things, scribble values that we're finding to see eventually how this comes together. Okay, so we're just exploring. All right, so as a summary, this is what we did. We said the voltage across R2 is called V2. It's not known yet, but it's just called V2. That means that the current through R2 is known. That's equal to, that means that the current through R2 is given by V2 over R2. If we find V2, we'll find V2 over R2. Then we said the current flowing through R2 actually happens to be the same as the current flowing through R1 because KCL has to be satisfied here. Then we said if the current through R1 is called V2 over R2, then the voltage across R1, this orange polarity, has to be equal to resistance times current. So we have that. Now we are ready to write a KVL because we have a loop. So we're going to start from here and write a KVL. Okay, start from here. I'm going from negative to positive, so I'm going to write this as minus Vx. I'm going from positive to negative, so I'm going to write as plus R1 V2 over R2. And then I'm going from positive to negative, plus V2, that is equal to 0, right? Because I came back to the same point. This is a piece of wire, so there's no voltage from here to here, right? So we have one voltage, another voltage, another voltage. That's it. Okay, so now we were looking for V2, and you can see that in this case, V2 is equal to, if I factor it out, is like this. So V2 is equal to Vx times R2 over R1 plus R2, right? So this circuit is actually an interesting circuit. Sometimes we use this combination of a resistor and here. We see that I apply the voltage here, and I got a voltage here. And this voltage is less than this voltage, as you can see from this equation. So we say we have attenuated Vx by this factor as we went to V2. So if you want, for some reason, to attenuate a voltage, you can use two resistors like so. The voltage to be attenuated goes here, and the output voltage is measured across R2, taken across R2, and that becomes an attenuator. So that's one little circuit that sometimes we use. Okay, so that was an example of the use of KVL, KCL, and Ohm's law. This concludes this lecture. I will see you next time.